Okay, so what I was telling you is, since the beginning of chapter 3, we were talking about bras and cats. And what is the advantage of having this notation, the cat, is that when I write like this, I could be working in any basis. You don't know in which basis I am. You don't know if I'm talking about a function in X, or if I'm talking about a function in momentum space, for example. Okay? It's only when I put this X or this P, then you say, okay, I know what she meant. So, but when you write it like this, it's pretty general. Okay? So that's one of the advantages of this notation, this cat. And so far, we've been just working with functions, position or momentum, but this notation could also mean a vector, a discrete vector with many components like this. Okay? Today we'll be solving a problem that uses now this kind of vectors. So this is new. It's simple, it's easy, but it's this new notation, okay? It's in a way, I think it will be easier than what we've been doing so far, because vectors and matrices, since high school, okay? But let's talk a little bit more about this notation before we start. So let me get rid of this. So if I have this vector, when I put it, so when I have this cat, when I put it together with the bra, I have now the bracket, this inner product. If it's normalized, we know it's 1. Well, what does it mean? So the cat is that column vector. I'm going to put 3 elements if I was in a space that is 4 by 4. Now, so this is the cat, is the column vector, while the bra is the row. And we have to be careful because these are all conjugates. So what this notation is telling us, well, exactly what I wrote here, the product between the row and the column. And this is going to be the sum 1 by 1, which if the vector is normalized, it will give us 1. Okay. All right. Now, suppose, like, coming back to vectors as you used to know, like vector velocity or acceleration, any of these more familiar vectors that you know since general physics. Now, so suppose I have this vector here. If I choose some frame, basically, if I choose some basis, I could ask you, what is the projection of this vector in the x direction? So this is the x direction. So what is the projection? You say, oh, easy. The projection is going to be just this part. Okay, so if I ask you, write the vector, the part of the vector r that is only in the x direction. Now, so this is the vector that is only in the x direction. So what I did here is a projection. That's what we call. Now we project the vector just in the x. So what is behind this procedure? I did a dot product between the whole vector and the x direction. So this gave me that the number associated, the size of the vector in the x direction, and I put it here, the direction. Okay, so this is my new vector. Sounds like too trivial, but I'm doing that just to introduce to you what we call the projection operator. And so the projection operator, we use this notation beta bit. Okay, so this is, so it's, now it's funny. Now, so this is the bra now, and this is the cat. So what is this notation telling us? Exactly what you saw here. What do I mean? Suppose I had a vector alpha. Okay, I have this vector alpha just as we had so let me put it here. I have this vector alpha, which is this column. similar to our vector R here. So now I have this column, this vector alpha, and I ask you, write just the part of this whole vector that is in the beta direction. So you do this projection of the alpha vector in the beta direction. So this projection will be beta, beta, alpha. This is the inner product. No? This is the inner product, just like here we had the inner product. And this is the direction beta, this is the direction I. Okay, so I'm saying all that just to introduce to you this very important in quantum mechanics, this projection operator. Okay. Okay, now if I have a certain set of non-linear, non-independent vectors. So if I have a set of all these vectors linearly independent, if I sum all of the projections, so I can have the projection on this direction, I could have the projection in this other direction. So if I sum all of them, then I change basis of the original vector that I had. So if I sum all of them, this is the identity. The sum of all the projections from a set of linearly independent vectors gives us the identity. In a way, I'm just giving you these names. When you do some kind of research or when you take a more advanced course in quantum mechanics, you will see how important these things are. The projection operator and the fact that the sum of all of them is the identity, okay? Very good. So given that, now I'm going to solve with you a problem, which is in this playing with these vectors, discrete vectors that I said. Okay, but before we go into that, let's remind ourselves what we've been doing so far. What we've been doing so far was the following. If I would give you some initial state, which means we prepare our system in some initial state, we would then ask you, okay, find this state later in time. So this is given, and now find this state later in time. This was many problems that you solved like this. What are the steps for being able to find the evolution of this state? There was a recipe that I gave to you in the beginning of chapter 2 already. And let me repeat this recipe, because that's exactly what we are going to use today, but now for a problem that does not involve functions like that, but involves those vectors. Okay, but what is the first step? The first step is solving Schrödinger's equation, the time-independent Schrödinger's equation, because we will need to have all of the energies and the corresponding eigenfunctions. So this is the step number 1. The step number 2 is, now that I have these solutions, I'll have to find a way to write this state in terms of those eigenfunctions. So that's what we used to do. And so we would have to find a way to write it as this linear combination, as this superposition of these states. Okay. Okay. And a very important step is, okay, how do we find then these guys, these components? You know very well. These components will be, we have our initial state. Here I'm going to put the solution of Schrödinger's equation, and we solve this integral. If you want to use the notation that we already learned in chapter 3, we would say, oh, that's what we need to do. Very good. So first step, solving Schrödinger's equation. Second step, getting these components. And then we are basically done, because now we can come, this is the last step, but now I can come here. The evolution will be that sum that we found, and now we attach to it those energies, the time dependence of the problem, and we are done. Okay, so I'm sure you remember this. You've done this many times, and that's exactly what we are going to do today, but not with functions. Okay, so if you don't have any question, I'm going to move. If I start speaking too fast, tell me to slow down. Since I'm not looking at you, I tend to speak fast. Okay, so I'm going to play with a size, a Hilbert space, but a Hilbert space that is very small. It's just 2 by 2. So the dimension that, well, I'll be playing with matrices that are 2 by 2, meaning the size of this Hilbert space, the vectors that I need to write any vector in this Hilbert space have just 2 components. So what is going to be my basis? A possible set of vectors that would compose my basis. I'll give them names. Okay, let me tell you, this is the example 3.8 in the book, okay? And this is very important, okay? So I'm going to write 2 vectors like this in this 2-dimensional Hilbert space, okay? Well, this is a good choice. Why? First, if I look at 1 with 1, I get 1. 2 with 2, I get 1. Huh? So they are normalized. And if I look at 1 with 2, I get 0. They are orthogonal. No? So this is a good, my basis is orthonormal. Which means with these 2 choices that I made here, I can write any vector that I want. So let me pick some vector S. I can write it in terms of those 2 like this. So this is A, this is B. Any vector that you want in this 2-dimensional space can be written in terms of those guys. So they form a good basis. And I'm going to use this basis to write the Hamiltonian. Okay, so my Hamiltonian now is not as we had before. No, we had that Hamiltonian with P squared, with potential and all that. Well, my Hamiltonian now is just a matrix 2 by 2. So in the diagonal, I'm calling this D and D. In your book, they call it H and H. I thought it was a bad notation because we have H for Hamiltonian. Then they put here, instead of D, they put H. And we have H bar, so it's a mess. So I'm going to put D and D. And in the off diagonal, I'm going to put this letter J. Okay, so this is the Hamiltonian that describes this system. And I started with this basis. So in this basis, I got those elements. Okay. And now comes the problem. The problem is the following. At time 0, we are in this particular state. So we start in this state. And now a question now is, what is going to be this state later in time? Uh-oh, Mika Kim. Okay. So I'm going to rewrite everything here. The Hamiltonian of this problem is this matrix 2 by 2. Our initial state is this vector, this column 1, 0. We want to know what is the state later in time. So I'm going to follow the recipe that we just said. We said, and put it on the side here. First thing that we have to do is solve Schrödinger's equation. I bet they didn't see they had not seen the email because they're coming on. Okay, so first step to do is solving Schrödinger's equation. And how are we going to do this here? When we did that when we were playing with the functions, well, we had to solve those differential equations. Now there are no derivatives, we just have matrices. So how are we going to do that? Well, is this the equation that we have to solve? So I'm going to start with this equation. I'm going to just call it S here. This is what I have to solve. Well, let's see how we are going to proceed. I'm going to bring everything to the left side. So I have the Hamiltonian. I'm bringing the energies also to the left side. But careful, the Hamiltonian is a matrix. E is just a number. So here I have the identity operator. Yeah, because I cannot subtract a matrix by a number. We have to play with matrices. So this is the equation that I have to solve. Well, now let me make a parenthesis here for something about linear algebra. Some of you may remember that. Some of you who had a linear algebra course recently will remember. If you don't remember, if you have never seen, don't worry. I'm explaining it right now. So let me call this whole matrix some matrix M. Okay. Well, if this matrix M has an inverse, the inverse of a matrix we denote by this. So if this matrix M has an inverse, this product between these two matrices give us the identity. Okay. Well, how do we get this inverse? The inverse of a matrix is a matrix that has the matrix of cofactors divided by the determinant of the matrix. Okay, well, so if it has an inverse, the multiplication gives us the identity. And how do I compute this inverse? I need to get the determinant of the matrix and use this procedure. Okay, so given that, let me come back to what I wrote there on top. If that matrix M, which is this whole thing here, has an inverse, what will, if I add, I can multiply the left and the right by the same matrix. What will happen is, since this is the identity, I will say that the vector is 0. So that's very bad. So I went through all this just to tell you, if the matrix has an inverse, I cannot solve this problem. It's a problem with no solution. There is no vector, there is no nothing. Okay, so that's not what we are going to do. So this whole matrix here cannot have an inverse, meaning the determinant of this matrix has to be 0. If the determinant of that matrix is 0, good. Good because there is no inverse. And I'll be able to solve this problem. I'll be able to solve Schrödinger's equation. Okay? All right, so all that at the end boils down to the following. I have to guarantee that this matrix here, the determinant of this matrix is 0. Okay? So we need to guarantee that the determinant of that matrix, which is the Hamiltonian minus the eigenvalues that I want to find, that this is 0. Okay? Okay, now, you may remember what a determinant is, but if you don't, doesn't matter. You're going to be learning it right now. Okay, so we use this notation, this straight line, to indicate a determinant instead of the parentheses from the matrices. So here I have D from my Hamiltonian, but because of this part of the energy, I put minus E. Here I have J, and in the diagonal D minus E. So this has to be 0. So this means determinant has to be 0. What is the determinant of this matrix? It's very easy when it's 2 by 2. You just have to multiply this diagonal, okay? So you get D minus E squared. And now you multiply the other diagonal, but with a minus sign. So here, minus J squared over 0. This is the equation that we have to solve. If we solve this equation, we'll have our eigenvalues. We'll have the energies of the system. Okay, so that's the procedure. Okay, how do we solve that? You can open the square, this is a quadratic equation, but there is a trick that is good. If you stop to look at a little bit at this equation, look, you can write it like this, D minus E plus J, D minus E minus J equal to 0. See that this is a good way, because then instead of solving the quadratic equation, you can say, this has to be 0 or this has to be 0. So you can find E directly from that. So let's find E from this equation. One possibility then is that E is going to be D plus J. From this equation, E is going to be D minus J. There you are. We found our two energies. Okay. Now, this is the first step. So let's come back. Remember what we are trying to do. We are trying to solve, Schrödinger's equation. In this case of a matrix like that, discrete 2 by 2, what did I have to do? Find the determinant, or make sure the determinant of this whole thing is 0. By doing that, we found the eigenvalues. Okay. Now, since there is a negative sign here and positive here, just I'm being picky here. You give the name that you want for these energies, but there is a chance that this one is smaller. So I'm going to put 1 for this guy and 2 for this other one. Okay, just like this is probably my ground state and this is my first excited state. Good, but that's not the end of the story, right? Here we just found the energies. We still need to find the associated eigenstates, what eigenfunctions. I have to find this eigenstate and this other eigenstate. How are we going to do that? If we have the energies, we just have to go back to our equation. What is our equation? Hamiltonian acting on a state. The state doesn't change. We just get a number in front of it. Okay. I know what these numbers are. Is either this one or that one. Huh? So that's exactly what I'm going to write. When I act the Hamiltonian, when I act with this matrix on this vector S1, nothing changed. I will just get back S1, but with a number in front, which is this energy here. So D minus J. And on the other side, when I act on S2, nothing changes. I just get a number in front. Okay? This means to have this the solution of Schrödinger's equation. Very good. Now we are there. What is S1? What is S2? I don't know, but I know it has to be a vector with just two elements. I mean, this two-dimensional Hilbert space. So what we are going to do? We're going to rewrite the Hamiltonian here. And in the place of this vector S1, I'm going to put two letters, two symbols there. I don't know yet what it is. I put these two symbols and I'll try to find. Okay. So This is what Schrödinger's equation tells me. What I need to find now is what is A and B that satisfies this equation. So what is the A and B that makes this vector being an eigenvector of this Hamiltonian? So how do we go? D multiplied by A plus J multiplied by B. So this is what I'm doing here. Equals to the first element, D minus J, A. Equals to this first element. The second line, J, A plus D, B equals to D minus J, B, the second. Okay. All right, so now this is what we have to solve, but look, many things that here have dA and here also have dA. Now at the bottom, I have dB and dB. So you see that this equation, these two equations became JB equals to minus JA and JA equals to minus JB. So we don't need this J around. What we see is that A is equal to minus B. So my vector is A and minus A. So you see here, B is equal to minus A. So I wrote that. Good. So this satisfies this set of two equations. So this satisfies the Schrödinger's equation. But still, what is missing is what is A? We know how to do that. We are after vectors that are normalized. So I go A, 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 and A. This has to be 1. So what I did here was to write S1, S1. Has to be 1. So this is the vector that I just found, but it has to be normalized. So then I have first term, absolute value of A squared, second term, absolute value of A squared. What I'm doing is this, equal to 1. And then you see, this is going to be 2. And so A is 1 over square root of 2. Long procedure, but then we finally found S1 is 1 over square root of 2, 1, and minus 1. Okay, so now we have the eigenvalue, D minus J, and the corresponding vector, this S1. Okay, so I'm going to write it here. We found that for the eigenvalue, for this energy, D minus J, the corresponding vector is this 1 over square root of 2, 1 minus 1. And so you see, remember, we are still in the first step of the procedure, which is solving Schrödinger's equation. Well, but there is another eigenvalue. This other one here, the D plus J. So we also have to find now this other eigenstate. And the procedure is still the same. So this part is not hard. Now we have to write the Hamiltonian again. I don't know, we don't know yet what the vector is. So we are going to guess some AB. We are going to use now this product of matrix and vector to try to find this A and this B. So let's go now. D multiplied by A plus J multiplied by B is the first line. The second line, D multiplied by A plus D multiplied by B. Okay. Again, you see that some of these terms cancel. Now this is dA and this is also dA. Here we have dB, and here we also have dB. So you see, and J is the same. So you see that we end up with B equals to A equals to B. So very similar to what we had before, just a sign that change. So our vector is AA. Again, we have to guarantee that it's normalized. So we have to guarantee that this is going to give us 1. So same procedure. And we are going to find that A is 1 over square root of 2. Okay? As we did before. So this other eigenstate is very similar. The only thing that changes is that this is 1, 1, while here we had 1 and minus 1. Okay, so then that's the end of the solution of Schrödinger's equation. We have these two eigenvalues, d minus 1 and d minus j and d plus j, and the corresponding vectors, the corresponding eigenvectors or eigenstates. These are all available terms, okay, possible terms. Good. So that's the first part. What comes next? So this is step 1. Step 2 is okay. The initial state is this. So let me put a capital S to distinguish. So our initial state is this one. What do we have to do? We have to find a way to write this state in terms of those eigenstates that we obtained, as we used to do. Well, here we have just 2, so I didn't need to put the sum like that, no? But just for you to remember how we were doing. So we just have to write a sum like this, which means we have to find a component for the S1 vector and the component C2 for the S2 vector, eigenvector. Okay, this is such a simple scenario, no? Because it's just a vector with 2 components. You could go straight for this equation. C1, what is the vector S1 is here. And the vector S2 is here. So this is what you would have to solve. Now, it's up to you what you prefer. If you want to go like that, or if you want to follow what we used to do, which is the same thing. But what is it that we used to do? We would put C1 is the inner product, no, the bracket between S1 and the initial state. And C2 is the same, but now with S2. Okay, so either you go solve this equation directly, no, you will have sums of C1s and C2s, or you find each C1 and C2 using this one. So remember what we used to do. Cn was this, integral, which is the same thing as psi n with psi 0. So this is what I'm writing here. Very well. So I'm going to erase this. To find this component C1 and C2, I have to play with this inner product, which is very simple. What is S1? 1 over square root of 2, vector 1 minus 1, right? And S0 is my initial state. Big S0 is my initial state, is this. So you see that what survives? 1 over square root of 2. So this is our C1. What is our C2? Very similar, but now the S2 is 1 over square root of 2, 1 and 1. But you see, again, we get the same value. The same 1 over square root of 2. Okay, so second step done. We found that our initial state can be written in terms of those eigen states, those eigenvectors, as C1 is this, so I'm going to put it here. This is C1. This is S for the vector S1. And C2 is the same, so C2 is the same value. And then we have here S2. Okay, so that's our initial state written in terms of the eigenstates of the Hamiltonian. Now I'm going to make a parenthesis here, okay? Now this third step will be to find the evolution, okay? But before we go into that, let me make a parenthesis to tell you something. Well, first, if you look at what we have here, our initial state was 1, 0. Now we are writing in terms of S1 and S2, but it remains 1, 0. The vector never changes. What we are doing here is we are changing the basis in which it's written. Because look at this. If I write this, what S1 is, 1 over square root of 2, 1 minus 1. And I have this 1 over square root of 2 here for the C1. Then here I have 1 square root of 2 for the C2. And what is my vector S2? 1 over square root of 2, 1, 1. You see that if I check what this whole thing is, what do I have? 1/2, 1 minus 1, plus 1/2, 1 plus 1. What do I get from this sum? 1, 0. So I get to the same original vector. So this is a parenthesis, no, but this is a good check also for you if you want. Did I get the components correct? Yeah. So what is the story? We started with a Hamiltonian written like this. Okay. And it was written like this because we played with the basis, with those linearly independent vectors that were 1, 0 and 0, 1. Okay, so in this basis, that's the Hamiltonian that I get. Now, I can always choose different bases. If I write my Hamiltonian in this other basis, the S1 and the S2 that we found, the same Hamiltonian becomes now D minus J, D plus J. So it becomes diagonal. Okay? When I use these guys, the eigenstates of the Hamiltonian as the basis, the Hamiltonian is diagonal. So this procedure of solving Schrödinger's equation, of finding the eigenvalues, is what is known in linear algebra as the diagonalization. So it's the procedure that we do, it's like a rotation in this matrix to put it in a diagonal form. And what are the basis that guarantees that? The eigenstates of the Hamiltonian. So whenever you have a Hamiltonian that is already diagonal, let me put here A, B. Well, you don't need to do anything. It's the eigenvalues are just A and B. Okay, it's only when there are elements in the off diagonal, then you have to do this whole procedure called diagonalization to find the eigenvalues. Okay. All right, so let me just then continue. I don't know if I'm talking too fast. It's all being recorded. Okay, so now that we found our step 2, we found our vector. And we wrote our initial state. in terms of the eigenstates of the Hamiltonian, all we have to do, evolve. And to evolve, we know, is just attaching the exponential. So here is going to be exponential of E1, and for the state S2, the exponential of the energy 2. And that's the end of the story. But let's play a little bit more. Let's manipulate this a little bit more and put this in a vector form, okay? So our evolved state is 1 over square root of 2, that's the C1. From the vector, we have another 1 over square root of 2, 1 and minus 1. Now this energy is G minus J T over H bar. Okay, and then 1 over square root of 2 is the C2, 1 over square root of 2 from the vector S2, 1 and 1, and here we have minus I D plus J. Yeah, I'm going to put all these in a single vector. Okay, so let's see. 1 over square root of 2, 1 over square root of 2 gives us 1, or 1/2. So 1/2. Now look, for the exponential, this part with the d is the same for both. So I'm going to put this whole part in front of my vector. So I have both terms have minus I d t over h bar. Okay. So the part in red is what I'm putting in front because both terms have the same thing. And now I'm trying to write a single vector. 1/2 survived, now for the top element with, in the first case, in this case here, I have E plus I J T over H bar. For the second part, I have exponential minus I J T over H bar. Okay, so this is the top element at the top. The element at the bottom is again 1/2, but now careful, we have this minus sign. So I'm going to put here minus plus I J T over H bar. And then the second term is positive, and I have minus I J T over H bar. So why we are doing all this? Maybe because now you can recognize things. This top part here, exponential plus I, exponential minus I. So what we have at the top is exponential plus I something plus exponential minus I something divided by 2. This is cosine. Okay? So that top there is a cosine. I'm going to erase this and I'm going to write it. And so let me repeat. Once we reach this point, we were done with the problem. We are now just writing it in a single vector because there is more than we can extract from this solution. More physics. So what do we have at the top? Cosine of JT over H bar. Okay, how about the bottom? The bottom looks like a sine, but it's not a perfect sine. Let's remember what a sine is. I'm gonna put it here. So sine of theta is A plus I theta minus A minus I theta divided by 2I. We have the 2 there, but we don't have I, so I'm going to put I here and here. Well, if I put it, I have to remove it. And and you see that the minus sign has to be with the negative exponential, while here is with the positive exponential. Fine. So then what I have is minus I sine of jt over h bar. And now that's the end of the story. Okay, just double check. Yeah, so looks good. And you may wonder, why did we have to go through all this? This is very nice because look, that initial state, 1, 0, we could see it. We'll come back to this story again later, but we could have seen it as a spin that is pointing up, for example. Okay, so at time 0, it's a spin pointing up. But as time passes, this spin is rotating. Cosine and sine is telling us that it is rotating. Okay, so that's the solution of this problem. See, at time 0, we are at the state 1, 0. No? So if I put time 0 in our solution, the sign disappears, we just have the 1, 0. Later in time, let's say jt over h bar equals to pi over 2, for example. And so at this later time, you see that the vector goes all the way down. Now, you may say, wait a second, but how about this exponential? How about this minus I? You're right, I'm going to put this minus I here. I should have, well, at time 0, this is really 1. At later time, there is an exponential that I should put here. But what do we care about? Is probability. Is the absolute value square of this. When I do absolute value squares, this minus I will become 1. This will become 1. Okay, so the probability is just not these i's, they all disappear. So this kind of thing is what we call a global phase, something that doesn't carry information. It's not important because we care about probability. So about this term, an exponential of I for the whole vector is not important. It's just a global phase. Okay, anyway, so this kind of vector, this solution, is describing like a spin that is rotating around. At times 0 is like this, and it's rotating forever, like that. Okay, okay, so this is the end of this problem. Now, let me keep track of time. Okay, now I need to tell you homework for next Tuesday and how you're going to solve them, okay? So the problems will be, you just write it here, 3.40, yeah, 44 and 46. Oh, there was another one that I had seen. Well, these are the most important ones. Let me write it here. So these are problems to be done for next Tuesday, okay? 3.44, 3.46, and okay, I found and 3.26. These are important problems. 3.44, 3.46 is the same thing that we've done, but there'll be more things for you, more details there for you to catch. And so tell me if you have any doubts. Okay, but what is important is that instead of 2 by 2 matrices, you'll be playing with 3 by 3. And so I have to remind you of how to do determinant for a matrix that is 3 by 3. Okay, so remember what is the procedure. When we are trying to diagonalize the matrix, when we are trying to solve Schrödinger's equation, what we have to do, we have to guarantee that the determinant of this whole matrix is 0. Okay, so how do we do the determinant of a 3 by 3 matrix? Some of you may remember. If you don't, here it goes. So let me pick my matrix. I'm going to write the whole thing. And well, we have all these off-diagonal elements. Now, how should we call these off-diagonal elements? I'll call it J and J. I'll call it J1 and J1, and J2 and J2 and J3 and J3. It doesn't matter. Okay, so it's a 3x3 matrix. And we have to guarantee that this is 0. How do we do determinant? I think many of you are used to do it like this. This is the matrix, but you repeat the first column and the second column. This is just to support the procedure. And then how do we go? Diagonal again. Okay, so multiply the whole diagonal. So A minus E, B minus E, C minus E. Now we go diagonal by diagonal. Now let's pick the next one, this other one, plus J1, J2, J3. Okay, now the next, this diagonal. It's again J1, J1, J2, J3. Oops. Now we go off diagonal, and this will carry the minus sign. So we go like this, but with the minus sign. All this is part of the same equation, okay? So what I'm going to put here, minus J1, J1, C1 minus E. The other one, minus A minus E, J3, J3. And the last one is this, okay? So minus B minus E, J2, J2. All this equal to 0. Okay, so this is the kind of equation now that you will have to solve. You will see that many of the elements in these matrices for the problems will be 0. So many of these terms will be 0. It's not as bad as it looks. But the important thing is, you see, what we have here, if you open all that, you would have a polynomial of third order. That's important because now we will have 3 eigenvalues. Okay, but that's the procedure, and solve these problems. They are very important. Okay, so this is the end of chapter 3. And if you don't have questions, I'm going to start with chapter 4. Okay, so I don't hear anyone, so I'm going. Chapter 4 is the conclusion of this course. Super important is when we are finally doing something real, solving a problem that is real. The purpose of chapter 4, I told you in the beginning of this course, is to solve Schrödinger's equation, but now for the hydrogen atom. That's where we are going. And that's real. It's one of the few problems that we can solve analytically. We don't need a computer. Okay? Now, what is going to change? So far, we've been playing with just one dimension. Now we are going to go to the real world. Now the atom is in 3 dimensions. So we are going to play with 3 dimensions. So before I start talking about the hydrogen atom, let's talk a little bit about 3 dimensions. Okay? Okay, so what does it mean? So I'm going back to functions. Now we just solved some problems with those vectors, discrete vectors. Now I'm going back to functions because we are going to be solving the Schrödinger's equation for the hydrogen atom. What does it mean? So I'm starting here with the time-dependent Schrödinger's equation that you already know very well. Okay, what is this equation? Here, Hamiltonian, our operator Hamiltonian. What changes with respect to what we used to have? Well, this function now is not function just of x, it's of x, y, and z, and time. So this means that the Hamiltonian is not going to involve just one derivative in the x direction, but also in the y and in the z. And the momentum operator that we've been playing with. Now there is momentum in X, in Y, and in Z. Okay. So what is the Hamiltonian? The Hamiltonian had those, the second order derivatives, right? So let me write it here. First, we had that constant h bar square over 2m, and then comes the derivatives. But not just in x, I also have y and z. This is the part coming from the momentum, no? The kinetic energy, the p square over 2m. But now it's px, py, and pz. No? Then the potential will now depend on x, y, z. It could even depend on time. It will not be the case, but it could. So let me write the whole thing here in general. Okay, it will not depend on time. We never solved any problem in this course that it would depend on time. So I'm already removing it. How about this guy here? You may have seen in some courses that you had before, we call it the Laplacian, just to make our life easier instead of writing this whole thing. So then our equation, the equation that we have now to solve, will be this. Just as before, we are going to get rid of time, and to solve then this problem, we'll do using the separation of variables. We are going to do this next, but let me just tell you something about normalization. How did we use to check normalization? By solving this. Well, now it's x, y, and z. And so x, y, z, all this, the integral in x, the integral in y, and the integral in z. Okay, has to be 1. Again, to make your life easier, we can write it as an r and say that this is the derivative in, the integral in all of the components. But this is just notation. Okay, so but you have to be careful. If you're going to normalize, you have to do the integral in all 3 directions. All right, now coming back to this equation. Just as we did in the beginning of chapter 2, separation of variables, because our potential energy does not depend on time. Very good. So we know that we'll be able to split this time-dependent Schrödinger's equation. We'll be able to split in 2 parts. One that only carries the information about time, and the other which is the time-independent Schrödinger's equation. Okay, so our equation, the time-independent part, is this. Well, I should change this notation. Huh? Remember, we use this, the capital letter to indicate that we have something that depends on time. And I'm using the small letter, the small psi, to indicate the part that depends only on position. Okay, so once I solve this equation, the time independent, I can find the whole solution just by attaching the energy to this story, as we used to do before. Okay, but the problem now is, how are we going to solve this equation? Well, just as before, we needed to know the potential. That's the only way we can solve this equation. And potential can be very complicated. What we are after is the hydrogen atom, is what our the big goal of this chapter is the hydrogen atom, which is the kind of potential that we call central potential. It's just a name, but which is easier to understand if I move, instead of playing with the coordinates x, y, and z, let me go and play with spherical coordinates. So what is this story? Well, let's put our frame. 3 dimensions, so I need 3 directions. So x, y, and z. Suppose I have a certain vector here. How do we indicate this vector? How you explain this vector? Now all the directions, you need an angle here, the angle theta. You need an angle here, this projection, this angle phi. Let's see if I... Yeah. So this angle here is the polar angle, and this is the azimuthal angle. These are just names, you don't need to know all that. Yeah. And then we have the size of the vector. Let's say r. Okay. What does it mean, central potential? That's a potential that depends only on the distance r. So, oops, in general, our potential could depend on r, theta, and phi. We are assuming that it does not, that it depends only on the distance. This is exactly what we have in the hydrogen atom. No? What is the kind of potential that we have there? A potential that depends only on the distance. No? Remember when you learn about Coulomb forces and the Coulomb potential, that's what it is, 1 over r. It doesn't have any information about angles. Okay, and so that's a big advantage. We don't need to play with those angles. No? And now what is the step? The next step? Well, we are going to solve this equation, assuming that the potential depends only on r. And it's going to be much more convenient to be playing with spherical coordinates. So that's why, forget about x, y, and z. Now we are going to spherical coordinates. But before we go into that, let me just say something else about the x, y, and z that I didn't mention. I said that now we have px, py, pz. When we look at the commutators between x and px, good, is what we used to know. But if you look at the commutator between x and py, these are completely independent things. It's 2 different directions. So this is 0. Okay? So just uncertainty principle and all that will be x with x, y with y. Okay, okay. So I'm going to move. So this was just a comment. But there'll be some problems for you to solve later about this. Okay, so this is just a comment. So I'm going to go now and try to solve. Well, we're not going to solve in 1 day at all. You'll see that will take many days for us to solve this problem. But I'm going to start thinking about solving the time-independent Schrödinger's equation. Solving this one. Again, I put the wrong symbol. Okay. So this is the one that we are going to try to solve. And I forgot the potentials. Let's put it in red here, well, let's put it like this. And let's put it in red here, that the potential depends only on R, is a central potential. So as we said, best thing is to write everything in spherical coordinates. So I'm going to rewrite this equation. Now remember the Laplacian there was in x, y, and z. No? So I'm going to rewrite this equation now in spherical coordinates. And that's something that you may have seen. You probably saw sometime in your life, I'm going to just write this. I see that is already 12:07. And then we continue next class, okay? But the Laplacian in now spherical coordinates, it's a long thing. 1/r², I'm copying ddr, r² ddr. So this is the part depends on r. Then comes the part on theta. 1/r² sine of theta, dd theta, sine of theta, dd theta. And then comes the part with phi. And that's sine square theta and the derivative in p, second order. Okay, so all this, of course, you don't need to know that, huh? But all this is what we are going to have to use now here to write our equation. So let's, okay, maybe, yeah, well, let's write it. Should I rewrite all that? We don't gain much by doing this, no? Anyway. So then I can just conclude the class like this. What is going to come now? The psi. And so we'll have to do this derivatives, all these derivatives for the psi. Don't even have enough space to write in the tablet. Then the potential and the energy. Okay, so this is the equation that we'll have to solve. What is going to be the next procedure? Well, just as we did before, remember that we did separation of variables. Why? The potential, we said, does not depend on time. So we were able to separate the equation and split the time-dependent Schrödinger's equation into one that depended only on time and one that had all the information about direction, positions, and all that. Okay, this is what we already did. Now, we are in this second step. We have a potential that, in principle, it could depend on r, theta, and phi. But we are saying, no, it does not depend on the angles. So again, we can do separation of variables. Yeah, just as we did before. So remember, before we said, well, my function is x and time. Because the potential does not depend on time, let me try to write it just x and something that depends on time. That's what we did. Okay, now, so this is chapter 2. Now, we started we already did this separation. Now, what survived in this story is this function. Okay? But I'm saying that the potential does not depend on theta and phi. Okay, so then I can try to separate the variables like that. Did you follow? Huh? So now I'm going to try to split this long equation into one part that depends only on r and another part that depends only on the angle. I'll try to do that because the potential does not depend on the angle. So very similar, analogous to what we had done to separate position from time. Now we are going to separate this distance from angles. Okay, so let me stop recording